Okay, now, welcome to the Structure Modeling Conference. This is May 20th. Kevin Dye will be presenting part-whole relationship. Take it away, Kevin.
Okay, so this is the second part of the part-whole relationship discussion. Now I'm going to screen share, right?
Yes, please do that.
Okay, so last time we talked about the logical properties of the part-whole relationship. And this time we're going to talk about language properties. And then if we have time, we'll get into talking about object-oriented programming and UML. And that the reason is because we're interested in how to use interpretive structural modeling to do SysML, or the systems modeling language. So you see the you see Meronymy on the screen, everyone?
Yes.
Okay.
Yep, I see it.
Okay. So in the discussion of the logical properties, we talked about proper parthood being transitive, asymmetric, and irreflexive. There are non-transitive mereologies that have other properties, and the reason I started doing this work is because Joe wanted to go beyond the partial order, which is transitive, asymmetric, and irreflexive, and get into other combinations of properties. I started looking in the parthood relationship to see if there were other parthood logics that, for example, had non-transitive as one of its properties, and there are, but I'm not going to get into it today. But another aspect of studying parthood relationships from a language perspective was motivated by seeming intransitivities. Like if an arm is part of a musician is part of an orchestra, we never say an arm is part of the orchestra. So why does language work like that? So to understand that, they typically look at 6 types of parthood relationships. The one engineers typically think of is the first one, component integral object, like a handle is part of a cup. But there's other types of parts, like a member is part of a collection, like a tree of a forest. There's portion and mass, like slice of a pie. There's stuff, what stuff is an object is made of, like the steel in a bike. The feature of an activity, like paying is part of shopping. And place area relationships, like there's an oasis, it's part of a desert. And
have you moved your slides?
Yeah, we're on the 3rd slide now.
I'm still seeing you're on me.
There's the top of the slide says Meronymy and there's a paragraph.
Right. I just see an arm is part of a musician. That's all I see. Arm is not part of an orchestra.
Oh, still on the first page?
Yeah.
Maybe it's because I'm in slideshow mode.
Right.
How's that? No?
No change.
Huh.
Right, it's not showing you in slideshow mode, so it didn't follow you into that.
Okay, let me try sharing the whole screen. Do you see one new one now?
Yes.
Okay. Now, in language, there's about 40 terms which are
Kevin, can you go back to that last one since we didn't see it when you were
this one.
speaking to
Yeah.
it?
Yeah. So the one we typically dealing with as engineers is the component integral object relation, like candle is part of a cup. And these other types of meronymy are also part relationships, and they're dealt with in different ways. Okay. Did you have a question about it?
No, that was fine. Just wanted to see the list.
Okay. So there's about 40 terms that are even more specific than part, and about 400 synonyms of the word part. So it's one of the things that makes something which would seem to be simple more complex. There's other ideas that are like the part-hood relationship that we often confuse with part-whole relationships, like possession, ownership, attachment, attribution, as well as inclusion. We're doing one specific type of inclusion, which is the meronymic type of inclusion. And this is the list of what you saw on the previous page, just with single word titles. So component integral, member of a set, portion of a pie, stuff an object is made of, and so forth.
So the spatial temporal class inclusion are on top of the 40 kinds of the 6 types? Is that?
Yeah, I'm not sure.
That's interesting taxonomy there. Okay.
Yeah.
So, Kevin, in this particular what you pointed out here is it's an interesting classification, but in natural language speech, and when you're trying to get a group to understand the same type of semantics, is that then all of these distinctions and differentiations made basically by context?
Is it made by content?
Context.
Oh, context.
Of which the communication is taking place.
Well, if we were to use like interpretive structural modeling in a group, we would set forth the context and say we are only talking about the following type of part-whole relationship.
Excellent. That's what I was looking for. Thanks.
Yeah, we would set the context and not deviate from that. So there's so this is a way of looking at these different types of part-whole relationships. Things are part of a structured object, or things are part of a non-structured object. Like an example of a non-structured object would be steel is part of a bicycle, or a slice is part of a pie. The structured objects is what we're most familiar with, the component complex relationship. There's a way to view the semantics of part wholes in terms of configuration. That is, if there's a functional role or not, whether the parts are similar to each other, like molecules of water. So a drop of water is part of a bucket of water. It would be a homeomerous type of part-whole relationship. And whether the parts are separable from the whole. So for example, you can't separate the steel from the bike. You'd have no more bike. And this is a cross-reference of how these properties play out for the different part-whole relationships. So you see the component integral object, like handle is part of a cup, is both functional and separable. You could remove the handle from the cup and you'd still have the cup. And the handle is a functional part of the cup. And the handle is different than the rest of the stuff that makes up the cup. So it's not homeomerous. Okay? I'm just going to leave it there because that's the thing we'll be studying. But I'm just providing some context that part-whole relationships, I thought when I first started looking at it, what little Warfield said about it, which was almost nothing, he implied you use the inclusion relationship. But set inclusion does not have enough properties to set theory is not strong enough to model a part-whole relationship, because there's other properties, like you don't want a part to be part of itself. You don't want a part of something that is part of something else to be part of it. And so these are questions we would want to rule out. It's you can't ask all possible questions with as set theory would imply. Just a reminder that the reason we're doing part-whole relationships, it's one of the two major ways our brain works, by dividing things up or by grouping by kinds. And that's what we see in object-oriented modeling. We have part-whole relationships and we have class hierarchies. So that was a bit on language. Now, another aspect of part-whole relationships is the psychology. And in psychology, they call part-whole relationships partonomies. That's your word of the day, partonomy. And when we talk about the psychology of a part-whole relationship, there's even stronger assumptions that go into that. For example, there's a connection between the appearance of something and how it works. Don Norman, the design theorist, called these affordances. And this connection between how something appears and how it functions promotes inferences in the brain. So the way you would model things in terms of how your brain deals with parts has some stronger implications. For example, in the psychological view of part-whole relationships, a part cannot be part of two different wholes. Now, that means you can only have a tree structure and not a network. And so that's an even stronger restriction than the than the logical properties that I went over last time. Another aspect is that there are typically only 3 levels of parts. Now, if you've seen an IKEA assembly manual, or to make a grill, for example, it seems like there's a lot more levels, but we typically divide things up into only 3 levels deep. And then there's three domains of partonomies, how we think of part-whole relationships of objects, scenes, and events. So temporal reasoning has, we divide things up in terms of parts. And also visual scenes, we tend to divide things up into parts. I'm going to skip this one. Now I'm going to talk about functions. What if you wanted to do part-whole relationships of functions? It gets even more complicated. For example, a wall is a structural part of a house, but the wall is not a functional part of the function of the house. It's a little confusing. It supports the house, but it's not a functional subpart of the function of a house, which is to be a home for people. So functions get more complicated. And it'll be important to look at functions because that's how we model systems in terms of functions, and objects and processes also depend on functions. When I was doing my work at the Center for Coordination Science at MIT, I was specifically studying how to model. I wanted to be able to do IDEF modeling with interpretive structural modeling. You familiar with IDEF modeling? I think Joe is.
Yes.
Yeah, so IDEF 0 is functional modeling. And what I wanted to move from IDEF modeling to process modeling. At the time, we were starting to use business process reengineering. This is the early 90s. We were doing business process reengineering, and we were hiring Japanese experts in total quality management to introduce process improvement work in non-manufacturing areas. We did them, we went big time on the Japanese techniques in the manufacturing sector in the 80s. In the 90s, we started trying to apply the techniques outside manufacturing. And so I was modeling processes, and a process has a beginning and an end. So it's an interval. And how do you do interpretive structural modeling with intervals? But had never been talked about before, really. They treated the work that Warfield did in what he called the delta charts, which was using ISM for doing PERT charts. He treated all the activities in the PERT chart as a point, which is a little confusing because you don't know if the beginning of the first process has to be, if you have 2 processes, A and B, in his technique, you don't know if A comes before B, if it's the end point of A that comes before the beginning of B, or does the end point of A come before the end point of B? It's ambiguous in Warfield's approach. And so I was studying how to do this, and temporal logic goes back to the Arab world in like the 6th century or something, they were wrestling with this. And it came back.
Do you have a reference for that 6th century work? Just can you give a name, or would we find it by Arab temporal logic 6th century?
Yeah, I'm not sure about the actual century, but Arab and temporal logic would probably bring it up.
Okay, I'll look for it.
What I was thinking is the guy that really did a lot of work to renew renew the corpus on temporal logic. He was out of New York. I think his name was Thomas Allen. Can't quite remember. But he would references it. If I think of it, I'll send you a note on that. So one of the differences in using part-whole relationships to model functions is that there's the temporal aspect of it. X is part of Y at a particular time. Right, so that's hard to capture in set theory. And so it's just another one of the complications of dealing with the part-whole relationship when it's applied to when you're dealing with functions. And here it's saying mereological language, meaning the logical approach to part-whole relationships that we went over last time is not expressive enough to model functional part-whole relationships. And it gets worse. If we look at object-oriented systems, something which would seem to be straightforward to model part-whole relationships for objects wasn't dealt with properly. They modeled it as a has-a attribute, and the parts were not, quote, first-class citizens. And the process, I mean, the notion of part-whole relationships is still vague in object-oriented modeling. It's associated with different terms. For example, aggregation, composition, assembly, containment, membership. They're all different approaches to part-whole relationships. And there's kind of a wide-ranging debate in the object-oriented community about whether the logical principles that we covered last time can be adopted in programming. This is I don't remember the reference 22, is that the basic principles of logic that we went over to model something as transitive, asymmetric, irreflexive, and then the additional properties such as supplementation, that you can't have a whole with only one part, that something that's a part of something that's part of something else can't be part of the first thing. These basic things are considered inappropriate when trying to model domains with object-oriented modeling. So you see the quote here is not able to account for subtle aspects of part-whole relationships. For example, the extensionality and some principles in logic maybe I don't want to get into too much of this. Let me skip to this. Another example is the object composed by John's left hand in the door of your house would not make sense as a part-whole relationship, but the logical treatment of it would be fine with that. But there's in the logical approach to part-whole relationships, as well worked out as that is, it wouldn't care if you talked about, John's left hand is in the house and the door is in the house. That would make sense in terms of logic, but it doesn't make sense to us. So it's in some of the properties of logic are too strong, and some of it is too weak. And this is an example where it's too weak. So let's get an example here. So this is an example of, this is too detailed to get into at the moment. Let's go to UML. Okay, so the unified modeling language has two constructs that, two major constructs that are related to part-whole relationships, which are based on what they call aggregation, and they have different characteristics of part-whole relationships. So there's emergent properties, whether things are resultant properties, if there's asymmetry versus anti-symmetry, and then additional characteristics such as encapsulation, overlapping lifetimes, shareability, transitivity, configurationality, separability, mutability. So these are additional properties on top of the basic logic that we went over. And this is another view of those properties. So this is the properties of the aggregation relationship when you're trying to use aggregation to model a part-whole relationship. And I think I'll leave it there and open up discussion.
That's great. So I have a comment. And
yeah, very interesting.
I think the most general comment that I want to make is about the idea of object-oriented modeling. And object-oriented modeling from the software point of view, came out of the software area. What they're talking about there are executable objects. And so they're talking about specific type pieces of code that can be executed. And those specific pieces of code that can be executed can represent anything. Okay? So when we talk about object-oriented programming from a software point of view, in my mind, it does not map at all to anything in the real world as we see objects. They're just two completely different conceptual spaces. They mean two completely different things. So that's the first general comment. Second general comment is on the temporal logic. A.N. Pryor, on his book, Time and Modal Logic, I think it was. They published in 1957. He did a history of the philosophy, and it was mostly based on Peirce's work. He was a student of Peirce and time and modal logic, but he did go back and talk about the Arab piece, and that piece basically also Peirce did. but that's really an interesting history of that. So that's a good book, 57 A.N. Prior, Prior. So there's a lot of.
What's the
there's a
guy's
lot
name? Prior? Did you say Prior?
Yeah, Prior. Book 1957, Time and Modality. So the interesting things that we run into when we want to model real world physical object decompositions in terms of at an engineering level. Like I want to build a part of an aircraft, I want to build parts of a car or things like that. And that interesting things we run into there are the fact that there's a strong difference between the hierarchical decomposition of the physical parts of any specific system and the hierarchical decomposition of the functional parts of that system. And so from an engineering standpoint, if you are tasked to go design something that performs this function. And so you take a functional decomp, you say, okay, I'm going to design something that does all these things, right? Those two hierarchies are totally and completely different. And they create a tremendous amount of chaos in mapping across those two hierarchies. So, yeah, those are my general comments. I will let somebody else comment.
So yeah, along those lines, we also in the early 90s were interested in the IDEF languages and or methods. And I think of that, what you just described there, Joe, and what Kevin had alluded to as the IDEF zero problem, because there's a lot of discussion about how people get confused in the functional hierarchy, and because we impose structure on it. So these are really interesting issues to articulate, as part of the your whole project of expanding a systematic framework for Warfield's work. Let's see. Another thing I was thinking about the basic ways that our minds work. So grouping by kind, composition. Were those the two that you mentioned? Kevin? Yeah.
We group things by similarity, or we break them into pieces.
And so I think in the Lakoff and Nunez book, they also, about the metaphoric basis of mathematics, they also talk about traveling along a path as a root metaphor. And that gives you the temporal, the basic way that we string things together in along a path. So maybe it's helpful to think that we have three basic framings, and then we have these overloaded terms that are similar but different. And it's a very great presentation. A lot more there than you went into, and it would be fun just to stick on this for a while and get into more detail of the things that you were talking about. I can see that the two approaches you're tending to talk about, if you have a fairly sophisticated group where you can say, we're going to talk about this kind of part-whole relationship, and our system will constrain the questions that we need to ask. That's one application. The other is if you're working with an open-ended, messy problem, and people start to identify different kinds of part-whole relationships, and you want to have your system know it may be one of these 40 kinds, and so how do we disambiguate the overloaded terms of part-whole? Both of those would be really great uses of the technology.
Yeah, I don't know how to do the messy one. That's because one of the actually I'll go. One of the slides I had was spoke to that. Let me. Let's see. This is Dijkstra's notion of separation of concerns, and as basically as a discipline for modeling that. Well, let's just read it.
Yeah, I'm not seeing it there. I'm just seeing unified language. Modeling language.
Yeah, I can see it.
Separation of concerns.
Now I don't see it. Wait a minute. I did a minute ago. There.
Can you see it, Joe?
No, I don't.
Well, the basic idea is, as a discipline for modeling, to deal with one aspect of interest at a time. And in interpretive structural modeling, the implication of that is you're typically dealing with a set of things that are all of the same type, or at least you're going to treat them that way. So, for example, if you're identifying the challenges in a project and you're going to be coming up with actions to address those challenges, we would typically do an interpretive structural model of the challenges, and we would do an interpretive structural model of the actions, and then we would interconnect them all as separate processes. We wouldn't talk about the challenges and the actions together.
That's very interesting. I think the thing that's one of the things that's interesting to me, and I think this goes back to Sage's work. What Sage generally said, I think, is that interpretive structural modeling, one of its great uses is to organize your value system. You know, to prioritize your values, prioritize what's important. And so once you identify what the concerns are, right, then you want to, then you go through the process of separating them, then you need to prioritize them because you can't address them all at once. That's basically what I think he's saying there.
Yeah.
And so there's the process of identification, then there's the process of prioritization, and then you can address them. And so the key aspects of that, and in my experience has been, there are totally and completely different concerns between physical system representations and functional system representations, right? For example, let's say they want to be able to lift 120 tons in an aircraft, and I wanted to take off at this certain time and do these things, right? So you start prioritizing those things, first problem you run up against is say, okay, I got laws of physics that prevent me from doing this, right? And so you start prioritizing the physical thing. The functional hierarchy is not really, it's your imagination. You say, this is what I want done. Hierarchy decomposed, this is the world I want to see. And then when you start to actually transitioning that into real things, you run into the physical laws first. You say, oh, okay, that's simply impossible. So now when you find the possible things that you can do, right, then you start prioritizing those. Well, which is the most important to me, right? And I think that's that all tends to get all mixed up in most of the processes I've seen on very large scale systems. People do not make that distinction, and it becomes very difficult to separate concerns.
Yeah, could you repeat that distinction?
So what happens is, for example, let's say someone says, I want the capability to go to the moon by the end of the decade. Kennedy, right? And he says, I want to go to the moon by the end of the decade. That is basically a function that he wants done, right? And so now the task is to design the physical system and operations and organizational systems to actually get that done, right? And so those are two completely different functional decompositions. Once at the top, you say, go to the moon by the end of the decade. Okay, fine. Well, to do that, I got to break all those functions down, right? Now, the physical objects I'm going to have and the organizations I'm going to build and all the facilities I'm going to build to actually perform those functions also have a decomposition, and they're completely different. And so you need to prioritize what you're going to do first, right? You're going to develop technology first. What are you going to build? What are you going to do concurrently? What has to wait and be done in sequence? Things like that. And it's been my experience on large programs that most people don't separate things into those buckets. They just organize and go forward on a part that they're familiar with, and kind of ignore the boundaries, which then leads to problems with integration. So, does that make sense?
Yeah.
Well, one interesting thing you said there is you talked about values, which is neither specifically functions nor structures or objects. And so I think by expanding the scope systematically, relating values to functions and structures, one can have the proper place for these various things. It might need more than values to be added, but usually, well, I think if you don't have the people and their values in the picture, then you are more inclined to get confused between the abstracted view of function and the abstracted view of objects. But if you have the values and the people in the picture, then it makes more sense that the functions and the objects are both relevant to their concerns, which are dependent on their values in a given context.
Yeah, it can be. There's a lot of different interactions there, but I think one of the key aspects of ISM, I think hasn't been really highlighted too much before, and that's one is ISM is a very early on type of idea when you're dealing in a large scale program. Very early on, what you're doing is you're trying to discover the problem that you want to solve. What is this problem? Okay, the problem critique. What is the problem? There's a technique to do that. Then you say, okay, let's do our value structure. If we're going to address this problem, we need to have some kind of shared value system that we can use to decide what we want to do first, second, and third, because instantly, so we're constrained by time, And most all projects are constrained by resources. So you have to make some kind of decisions there. I believe what Sage was saying was ISM is one of the only techniques that has a structured way of doing that up front. And then you go on to other techniques after you've performed that, depending upon which way you want to go. You want to go to system dynamics, you want to go to, structured analysis, IDEF zeros, whatever you want to do.
Yeah,
Right.
that's a good point.
So Michael found the reference to the Arab work. It was Avicenna. Does he have another name?
Oh, yeah.
Ibn Sina,
S-I-N-A.
S-I-N-A, also known as Avicenna, right? So the prior work, given that it refers to modal logic, I assume it is based on Lewis's modal logic. Do you know? Lewis,
You're asking
Lewis,
me,
who
Joe.
first developed modal logic. What's that?
Were you asking me or Joe?
Yeah, everybody's breaking up a bit. So Lewis was a student of Peirce's as well. He was the one who first developed modal logic in the 20s. And he inspired Schuhart to develop his ideas about statistical control, which then Deming was influenced by. And I'm hoping you're hearing this, but so there's an interesting connection from Peirce to Lewis to Schuhart and Deming to quality management.
Yes, I'm hearing this well.
Janet, I think it's all very the connections are there. One of the things that I think that has impacted a lot of the work that's been done recently is the typical type of application we try to do with our tools. I think our tools, maybe since 1985 till now, have really impacted our application of logic in most cases because of the restriction of binary logic, basically Boolean logic in our basic computing system. But that's starting to change now a little bit. We're getting some better tools. They're being produced and available for everyone. But it's, I agree, sequence is very important. You cannot even have numbers without a sequence. So fundamentally, the idea of a sequence is always there. And the idea of a sequence is fundamental to the idea of priority.
Right.
So it's always there. We simply don't, most people, let's put it that way, most people don't consider the implications in their logic.
Right. The other question I wanted to ask Kevin, if I'm coming through well enough, is the idea of a property seems to be taken as fundamental in what you were presenting there in UML. And so I was wondering about what are the foundational assumptions about what a property is?
It's a good question. I'm not an expert on UML, so I'm not really sure how to answer.
Okay, so let's maybe I'll just take a couple minutes here and not talk about UML specifically first, but talk about object-oriented modeling first, object-oriented code. And basically, what they wanted to do with object-oriented code was they wanted to stop repeating all this procedural stuff, right? And so we had variables, so we could change the variables, but then, even then, once you had variable pieces, you might have the same pattern in the code that you used in 10, 15, 100, 1,000 different places. You didn't want to copy that, so you wanted to be able to actually reference that as an object. And that's basically the way object-oriented programming started. Then they encapsulated the object so that an object would only do one thing. And then you would send objects would talk to each other through messages, right? Object one, let's say object one displays a number. Object two, object one inputs a number, object two multiplies the number by 2, and object 3 displays it, right? So essentially, object 1 would just, okay, input this number, sends a message with a value to object 2. Object 2 then says, okay, I have this value, I multiply it, then it sends it off to object 3, right? And so depending whether you have a bus architecture or a hardwired architecture, these messages are passed. So it's just message passing going on, right? And it's very, very modular and allows you the ability to plug and play like Legos, right? So that's kind of the objects piece. And the object-oriented modeling, then what they're doing with these, when they're looking at the attributes and they're looking at it's kind of like a variable. So if I have a car that has 4 wheels, right? That's an attribute of the car. Well, my physical idea of modeling that over there, I have to have some type of attribute of this car, number of wheels, weight, color, things like that. And those then are things that you assign to the variables, right? So these are very much kind of software type of analysis. Does that make sense? Okay.
Yeah, it makes sense. I thought your question was to Janet. She was asking about properties. What is the what property?
Attributes, properties, properties essentially, depending upon which version, attributes and properties are essentially the same. One property of an object, you're going to have an attribute that's static and global, right? So they're essentially the same thing. You got functional properties, which are functions that an object does, and that's essentially the same idea.
I'm having trouble hearing, but yeah. So I was wondering about, is there one interpretation of the relationship between property and attribute, which gets back to your point about objects as executable code are not easily mapped to objects, common objects. So that's just another way of saying this whole modeling domain needs more systematic development.
So what happens there basically is it's kind of standardized by use. And so if you have a large object-oriented JavaScript library or Java or however you do that, right? Those terms and concepts will be finalized in the library you're working with. Certain language groups of people use different concepts on that, different semantic interpretations for that, especially languages like some of the very dynamic languages. For example, JavaScript, where you can do functional programming, object-oriented programming, procedural programming. If I have a language that allows me to do, multiple programming approaches in the same language, then those terms will be different. If I have one module I wrote in object-oriented, the next module I wrote in functional, the next module I wrote in procedural, they're all going to be executed by JavaScript and they're all part of my program. I'm not going to have a different word for an attribute or a different word for, a parameter or whatever for each one of those. And so that really, once you get down to actually into the community that uses that stuff, then they then strictly define the terms. But at the higher level, it's kind of fuzzy.
Good. Okay.
All right. So we have about another 6 minutes. So we're going to be getting the read ahead for June out, where we're going to focus on local and global relationships and the definition of those, and define that much more precisely, and then also try to bring more definition to the idea of a single thread and multiple threads within these ideas of a global and a local type of relationship. And then step back from that as we go forward and see if that's making sense so far. So it's one of the things I've been trying to. It's not clear to me that that we're going where we need to go with the technical reports. Is any feedback at all on the general content? Do people think it's going in the right direction? Is it might need to emphasize something else?
Definitely, yeah. I see it moving forward.
Okay. Well, this is the phase where we're going to drill down and talk about the theoretical components to local and global. Then we're going to basically start, in the next couple of months, start piecing that back together into code. So the goal there will be to make the distinction between the operations that are used to present the work that was done in the handbook, the ISM handbook, in the back page, in the appendices. So we'll at least do that. And we're still looking for a test bed, Kevin. Anybody have any code out there that they want to run examples against?
Yeah, I mean, we can run it here.
Okay. Have you run the examples out of the appendix in the handbook?
No, not on this software. It's a good point. I mean, redo it, but the problem with the handbook is it doesn't have a log of the yes and no's. I don't think.
It does.
Does?
Yeah. It tells you each answer.
Okay.
Yeah, I think it does. Yeah. So anyway, yeah, that would be a good.
So you're suggesting that to start with the IM handbook, it's in an appendix. Did you say?
Yeah, the appendix in the back, right? See if we can duplicate that. That'd be step one of the test.
Yeah, it's interesting when even between different codes, between Cognoscope 2 and Cognoscope 3, for example, they had to do the same problem, would have different sequence of questions, and it's because of the way that they calculate what they call an opportunity matrix.
Okay.
Right.
Yeah, I think that would be a great step if you could do that, and then we could talk about that. We could compare the differences.
Yeah.
Okay. Well,
that sounds good. That sounds good, Joe.
All right. So now we've got June. The next one's coming up will be June 3rd, right? June 3rd, 9 a.m. We'll get the read-ahead out. And thanks everybody for contributing. Thank you, Kevin, for doing the presentation.
Yes, excellent. Very good.
Now for June 10th.
Talk to you later.
We were going
June
to.
10th.
Were we doing?
June 3rd, isn't it? What's going on June 10th?
Well, we started doing the second week.
Yeah, so that would be June 17th, right?
Oh, 17th?
Well, let's see. We got June 3rd, right? And then 14 days. Let's see.
Okay. So it's the 17th. So I think the thing to move onto the two next biggest things to deal with to be able to deal with SysML is to get into how to use ISM for class hierarchies.
Okay.
And then the thing after that will be functional relationships or
Sounds
causation.
good, Kevin. It's really interesting stuff.
Yeah, that'd be great.
Okay.
All right. We'll see you all in a couple weeks.
Very
Thank
good.
you.
Bye-bye.
Well,